Welcome to the lectures on modern digital communication techniques. So, in the previous lecture we have seen the models of channel. So, it is the same thing that we have been doing before, but we have specifically looked at some of the things which we will need now when we look at the celebrated expression of channel capacity due to contribution of the great communication scientist Claude Shannon. And just a word of note that because of the contribution which we made, the whole field of information theory was developed, and it is a very interesting field, and it's involved with lot of mathematical expressions. It gives generally bounds on performance of certain systems. We'll take a look at one of the important results. Will not be very rigorous in our development, because our idea is to look at what's the end result is and how is it relevant for the study of communication systems. So, continuing with our discussion. So, now we look at the development of channel capacity. So, we consider a discrete memoryless channel. So, a discrete memoryless channel is something which we have been using before. That means, it has a set of possible symbols, right, discrete, it is a channel, and it produces a possible discrete set of outputs, and the output at a certain instant of time now is not dependent on what happened before. So, it is not dependent on what happened before, right. So, that is a memoryless channel, and the previous channel that we had seen was the binary channel. So, that means, it had two possible inputs. You could have m possible inputs if there are m points in the constellation. So, if you have if we look at the output of symbol mapper and the at the transmitter and at the receiver, we see the decisions with respect to the symbols, right, not the bits yet. That means, the constellation point, we have a discrete input, discrete output, and if it is memoryless modulation and the channel is without any memory, for example, just AWGN channel, then we have a discrete memoryless channel. So, moving further, the input alphabet is given by this. Alphabet means these are possible symbols which you could mark it as possible constellation points in PAM or QAM. In case of PAM, this will be real, in case of QAM, this will be complex. Output alphabet, again we are talking about alphabet. So, although noise is getting added, but still we are mapping the outputs to a particular constellation point, and transition probabilities are of course that is given there. So, in this case it is a probability of one symbol becoming another. So, that means, suppose I have 3D d minus 3D, and here also we have 3D d minus 3D. So, we are talking about what is the probability. 3D remains 3D, probability of being correct, probability of being error, probability of being error, probability of being error. So, we have transition probabilities of getting 3D given 3D, probability of getting D given 3D, probability of getting minus D given 3D, probability of getting minus 3D given 3D. So, we are going to have all these probabilities. Similarly, probability of 3D given D, and so on and so forth. We are going to get all these transition probabilities. And there is the definition of the term called mutual information. So, we will just use it without delving into much details. So, mutual information provided about the event x equals to x I by the occurrence of y equals to y I. What it means is that I have observed. So, let us say this is x 1, x 2, x 3, sorry, this is y 1, y 2, y 1, y 2, y 3, y 4. This is x 1, x 2, x 3, x 4. So, all it tells is that suppose I have made an observation, right. So, the mutual information is of the event that we observe y 1 and x 1 could have been the selected signal. So, instead of selecting y 1 and x 1, we say y I and x I, any particular symbol. So, what we have is given by the expression log of p y I x I upon p of y, y I x j, p of y I. So, this is x j, this is y I. So, for output is observed, one of the output is observed, what is the mutual information with a particular source symbol, right. So, this is the expression that is used, and P of y I is given by the event that the random variable y takes the value y I is P of y I conditioned on x k averaged over all possible x k. That means, for a particular output, that means for this particular output, the conditional PDF that 3D has been observed given 3D is transmitted plus probability of 3D has been observed given D has been transmitted plus probability 3D has been observed given SD has been transmitted plus probability of 3D has been observed given minus 3D has been transmitted. So, this is the total probability of 3D being observed. This is also straightforward. So, the average mutual information provided by the output variable y has to be about the input x, right, about the input x is given by. So, if you look at the extension is you are averaging the mutual information over all possible. So, this is the mutual information expression that you have, that is averaged over the joint distribution of x and y, right, over all possible x and y. So, this is averaged mutual information, and the capacity expression is defined as the maximum value of the average mutual information over all possible source probabilities. Now, this might appear a bit abstract, but we will have to live with whatever description we have here, because we cannot spend much time into the details of how these steps have arrived. So, anyway, we will still try to explain. So, the value of I x y, that means the average mutual information. So, effectively what we are trying to do is we are observing a particular outcome, and we are trying to find some kind of a correlation with what has been said. So, if we know that the probability of observing 3D is most when 3D has been transmitted. So, that in turn would intuitively mean that the mutual information between 3D and 3D should be very high, right. So, as noise increases, as there is more noise, there is more probability of 3D being observed because of other things, other source symbols, then the mutual information with other source symbols would increase, right. So, that is what it is trying to convey. So, the value of mutual information is maximized over set of possible input probability. So, what it says is that since you know the transition probability matrix, that is P of y given x, right. So, that is P of y given x, that is what we have. So, we would like to maximize the mutual information, that is we would like to maximize the correlation in some form, we would like to maximize the probability that whatever of detecting the right symbol from whatever we have observed, and you can do it by altering the probability of the transmitted symbols. That means, if I know the transition probabilities, that means, if I know that given 3D there is a certain probability that it goes to D or minus D or minus 3D, then probably I could play around with the probability of transmission of 3D and minus D and so on and so forth, right. A quick example could be that suppose I have 4 possible source symbols and I have 4 possible the destination symbols. So, what we try to do is, suppose this symbol becomes there is. So, let this be 3D D minus 3D, 3D D minus 3D. So, there is a certain probability of it remaining the same, there is a certain probability that it becomes D, and suppose the channel and the whole communication system is such that it does not become minus D and minus 3D. In a similar manner, suppose we take D, there is a probability of it becoming D and there is a probability of it becoming minus D, but it does not become minus 3D or it does not become 3D. Similarly, for this and similarly for this. Now, for this there is a certain probability that it becomes 3D. right. Let situations be like this. So, in this case we could roughly speaking do something like this. So, we would say that suppose, so now if all are equiprobable, we started with equiprobable discussion at some point, if all are equiprobable, then if I send D 3D and I get 3D, it is a correct decision, it is a correct situation. If I send 3D and I get D, we are getting into error. Same discussion follows for D to D and D to minus D and so on and so forth. So, but however, looking at the symmetricity of this particular constellation, we can probably say, so in one situation we have probability of 3D getting transmitted is 1 by 4, this also probability of sending D is 1 by 4 and probability of D is, let us say, 1 by 4, all of them are 1. Suppose this is the situation. So, it says that we want to maximize the mutual information on all these source probabilities. So, one possible solution could be that we, instead of choosing all of them, if I choose to have 3D being sent with a probability of half and minus D being sent with a probability of half, let us see what do we get. So, when I send 3D, it can become 3D, or with a certain probability it can become D, right. There is no D getting transmitted. So, D becoming D is not a problem. See what happens if, so now if I receive D, suppose I have received D, suppose I have received D. So, what is the detector going to do? If it receives D, the detector is confused whether the D has come because of 3D or it has come because of D. So, if I do not send D, whenever the receiver receives a D, it knows that D has never been transmitted, because probability of transmission of D is 0. I have modified this in the new domain with the new probabilities. I have selected a probability where I do not send D at all. So, being 0 means I do not send D, probability of minus D is equal to half, probability of minus 3D is again 0, right. So, now what you see is that 3D sent will be 3D or D. So, if I receive D, I am sure that 3D has been sent. So, when it receives minus D, it is because minus D has been sent, because D could also become minus D. Now, since D is not sent, we will always be sure that D minus D is because of this. Similarly, minus D could become minus 3D. So, when I receive minus 3D, again it is not confused, because it knows that minus D and minus 3D are produced only by minus D, and these two are produced only by 3D, right. So, by assigning these probabilities, you avoid any confusion and you would maximize the mutual information. So, that means you would like to maximize the mutual information over all possible source probabilities. So, that means you could choose any other combination, but if we choose this as one of the combinations, we avoid any kind of confusion at the receiver, right. So, this is all that it means. So, again in other words you can say that it makes probability of making an error almost 0, right. Okay. So, this is what it means, that the value of I x y is maximized over the set of input symbol probabilities p x y. So, you choose these things, in other words you are choosing the constellation. So, look at the connection. So, in this way you are saying that which possible symbols to be sent, which can't be sent. Now, this is because of the transition probabilities, right. So, how it translates is like this, that suppose this is 0, this is D, this is minus D, this is 3D, this is minus 3D, right. So, suppose it is wrapped around means here again you have, let us say 3D, it is wrapped around, suppose it is wrapped around. Okay. So, the conditional probabilities, how will they look like? The conditional probabilities would be like this, right. The conditional probabilities would look like this. So, sorry, this will be 3D, okay, if it is wrapped around, right. So, this maps to situation like this. So, when a 3D is sent, the probability of it being detected as 3D is area under the curve in this region, right. So, area under the curve in this region. So, I am going to get the probability of 3D being received as 3D, and the area under the curve here would be the probability of 3D being sent, but being detected as D, and suppose it goes to 0, right, it does not change. So, this is the probability that it becomes D, right. So, now you can easily guess, calculate or estimate even visually what is the probabilities of error in these situations, right. So, now going by this result, all it says is do not choose this as a transmitting symbol, right, and do not choose this as a transmitting symbol. So, if that is the case, our decision point would be somewhere here, and what we have is this completely going away, this is not present, right. So, if only 3D and minus D are available, in other words, we are increasing the minimum distance between the constellation points. So, if we are increasing the minimum distance between the constellation points, we are improving the error probability. So, in some sense it is relating to what we have discussed earlier. So, again when minus D is sent, since 3D is not sent over here, the probability of this becoming minus 3D is very less, and probability of it becoming 3D is also very less, because now you have the matrix going, the conditional probability matrix going away like this. So, this is gone and this is gone. So, you are left with this and this only, right. So, since the constellations are sufficiently spaced apart, the probability of errors have been reduced by appropriate choice of constellation. So, we have reduced the possible constellation. Now, this is because of the transition probabilities, and remember the transition probabilities are because of the variance of noise. If the variance of noise would have been different, right, suppose the PDF is narrow, the transition probabilities would be different and our result would have been different, right. Again, in the other hand, if we would have selected the constellation as let us say minus 3D, 3D and maybe minus 7D and 7D somewhere there, then possibly we would have had a situation where the PDF dies out and we could have existed with all the 4 constellation points. So, in other words, it is determined by the transition probability. So, given a set of transition probabilities, you are choosing the possible probabilities of source symbols, right. That translates to, given a kind of noise, power spectral density, or given the amount of noise that is present in the system compared to the received signal strength, that is the minimum distance, we are choosing the number of bits that we should send per symbol, that means the constellation order. So, this is how you could somehow relate to whatever this result is giving us and what we have studied earlier in terms of constellations and error probabilities, right. Okay. So, getting ahead. So, we have the capacity of the channel defined by the expression C, which is the maximum value of I x y over all possible source probabilities. So, you have the mutual information expression, again it is in terms of relative entropy, which we are not discussing, averaged over all possible x y combination, right. So, with this we move forward and see what does it lead to, and if you evaluate this expression for a binary symmetric channel. So, for binary symmetric channel you have 2 values of y only, this y takes 2 values, let us say 0 and 1 or plus 1 and minus plus a and minus a, let us say x also takes a plus a and minus a, like d or minus d. So, you can easily compute this because you know the transition probability matrix, and if it is a binary symmetric channel, the p, the probability of error, can be computed given the noise power spectral density. So, you are moving from the discrete input continuous output channel to a discrete memoryless channel. So, we can do these translations and we can compute these values. So, once you compute this, the end result that you would get is that the channel capacity would turn out to be minimum for the case where your P is half. That means, you have the channel capacity for P, remember it is the transition probabilities. So, probability of making an error is P, probability of making an error is P, probability of being correct is 1 minus P, it is 1 minus P, right. So, that means, a 0 remaining a 0 with 50% probability and a 0 becoming a 1 with 50% probability, right. So, that means, when I receive a 0, there is 50-50 chance that a 0 was sent, right. So, in that case it is equiprobable whether a 0 was sent or a 1 was sent. So, I would make no special decision, no special outcome if I choose a 0 or a 1, right. So, that is the worst possible scenario. Now, if I know that a 0 being sent and the probability of it becoming 1 is, let us say 10% only, then 90% of the time you can send signals successfully. So, that is what is conveyed over here. So, at a transition probability value of 0, capacity is minimum, you hardly make sense out of what is going on in the channel, right. Whereas, if your probability of error is less, as the probability of error becomes 0, it tends to a 0, that means 0 remains 0, it does not become 1. So, there is hardly any probability of error, your channel capacity is maximum, right. True, because there is no error, you can achieve the best. Counterintuitively, if the probability of error increases towards 1, that means, whenever I sent a 0, it becomes 1 for sure and it never becomes 0, it never becomes 0. So, that means, the bit is flipped, simply the bit is flipped, we are assured that the bit is flipped. So, 1 received means a 0 was sent and a 0 received means a 1 was sent, then again you achieve maximum value of channel capacity. So, that is what is displayed by this particular figure that we have over here. All right. Next, quickly let us look at the binary input AWGN channel. So, if we have the binary input AWGN channel, input is A or minus A, and you can calculate. So, let us just use this result that the mutual information is maximized for P, the probability of selecting the source symbols being half. Okay. So, we are not saying P is equal to half, mind it, P is equal to half is not what we are saying over here. We are saying that probability of selecting the source symbols is half. These are two very different things. Okay. And average mutual information between the input vector and the output vector in an AWGN. So, we have waveform channel, right. So, then we have this conditional probability matrix, and where these conditional probabilities would be given by an expression like this. So, if you fill it in these expressions, we can take a few steps forward, and we will be using these expressions, we will be using these expressions for conditional probabilities. So, if we carry on with a few steps, that means, we have to solve this expression. Previously there was no integration, there was summation because they were all discrete, but now since we have AWGN channel. So, waveform output, continuous output, we will be using these densities in our expression. So, evaluation is little bit different, but the expression in philosophy remains the same. So, when you solve this expression using these transition probability, using these conditional probabilities, what you end up with is an expression which I will not go through a few steps, but finally, you would work out it as the channel capacity C is denoted by W, which is the bandwidth of the channel, T, which is the symbol duration, log, this is base 2, 1 plus 2 times sigma x squared is the variance of transmitter times n naught, right. And sigma x squared, that is the transmit variance, one could calculate as 1 upon t 0 to t expected value of x squared t. So, this will be 1 upon t x summation over x I are the constellation points, you can say. So, this would turn out to be, if there are n such possible constellation points, this is the result, and you could summarize it with the average power by 2 w, right, because you have 1 upon T as W. So, you could use this result. So, if you fit this result into sigma x squared, what you will find that will end up with the expression of channel capacity, which is given by this C is equal to W log base 2 1 plus average transmit power by W n naught. Now, W n naught is the noise power P n, because n naught is the power spectral density, this is W in hertz, meaning you have the total noise power. So, what you have is W log base 2 1 plus signal power to noise power. So, in other words, sometime we will write capacity is equal to W is the bandwidth in hertz log base 2 1 plus S n r, and this is in linear scale. So, finally, if you do a few steps, and this is the famous result which Shannon gave us. So, we will use this as a benchmark. So, what it tells, what we have not discussed is, if we are given a certain transmit power, we know the power spectral density, given the bandwidth, we can calculate the noise power as n naught multiplied by W, that is the total noise power. So, average signal power by average noise power is the signal to noise ratio, plus 1 log base 2 of that is the bits per second. So, that means C upon W, C has a unit of bits, C upon W is equal to log base 2 1 plus gamma. That means bits per second, C is bits per second, per hertz, C is bits per second, or bits per channel use, sometimes we also call it bits per channel use. So, given a particular bandwidth W, you could use this particular expression to calculate the number of bits that could be sent per second per hertz. This is known as the spectral efficiency of the channel, right. So, with this one is equipped. So, now using this expression we could study the impact on channel capacity given a particular bandwidth W. So, what we have over here is, suppose you look at the expression C upon W is equal to log base 2 1 plus gamma. Gamma is the x axis, right, this is given in dB. So, it tells you as you keep on increasing signal to noise ratio, if right, what happens, your capacity or spectral efficiency increases. So, how do we connect? So, as we increase the signal power to noise power, right, we can increase the number of bits per symbol for PAM and QAM, right. So, this will tell us, the expression that we have seen, the maximum number of bits per second per hertz that you can send with almost negligible amount of error, right. So, this is a philosophical interpretation. Of course, there is a detailed derivation, as I told you, it requires a huge amount of time for that. So, we will just use this description. So, if we put in the value of transmit power and noise power into this expression, we are going to get the number of bits per second per hertz, or in other words, we can calculate the number of bits per symbol that we can compare with the QAM or PAM modulations in order to see whether we are doing a good job or a poor job. The next important result that we have with us is the situation when we keep on increasing the W. So, if we check this particular expression, that C upon W is equal to log base 2 1 plus gamma, we stated that if we keep on increasing this gamma, you keep on increasing C if we keep W constant, right, if I keep W constant. So, this is related to when we studied PAM and QAM. We said that if you keep time duration constant, that means symbol duration, W is constant, that is the bandwidth is constant, which is 1 upon T. So, if you increase the transmit power, you can increase number of bits per symbol, and this expression is going to give us the upper limit to it, right. Now, let us look at what would happen if we say that let P average transmit power by N naught W is the expression for gamma. So, if I say I want to keep this constant, right. That means, I am keeping P average constant, but I am increasing W, right, indefinitely. Then what happens, right. So, what we will see is I will just show you the end result, which we may do a little bit details in the next discussion, but briefly over here, that if I calculate the limit W tends to 0, what I will end up with is a value of SNR, which is minus 1.6 dB, right. I will do the derivation in the next class. So, what we see here is that from this expression also we are getting to the point, the limit of signal to noise ratio that must be maintained to do a meaningful communication, where W may be expanded to infinity, while power average P average may be kept constant. This we would remind us about the orthogonal signals, where we said that if you would keep increasing k, the number of bits, that means you will keep increasing m, that means you are keeping increasing the bandwidth, what is the limit on signal to noise ratio that you reach, and we did do the calculation earlier and we found that you could reach a value of minus 1.6 dB. So, let us look at this result in the next discussion. Thank you.